In this video, we're going to walk through the solutions to 4 practice problems related to gas behavior and the ideal gas law. So if you haven't tried those, take a pause, give them a try, then watch this video. So our first problem is about a balloon, and it contains 2.5 liters of helium gas. The pressure of the room's 1.04 atmospheres with a temperature of 260 Kelvin. Now, if the temperature is decreased to 180 Kelvin and the pressure remains the same, what will be the new volume of the balloon? I like drawing pictures for these ones. Note that it's comparative, and that's important when we think about what kind of equation we're going to use. So we have a balloon, and it's at a volume of 2.50 liters. It has a pressure equal to 1.04 atmospheres, and it's at a temperature of 260 Kelvin. Now, a change is going to occur. Temperature is going to decrease. And we're going to need to calculate our new volume. So we don't know the new volume. We know that the pressure is going to remain constant and be 1.04 atmospheres, and that our temperature is dropping. It's dropping all the way down to 180 Kelvin. And so we need to calculate the volume. So first, before we even plug values in, we should predict if this is going to get bigger or smaller. And let's remember our relationships that we explored about our different gas properties, physical properties. And when we looked at temperature and volume together, we saw that temperature and volume were proportional to one another. That means if we decrease the temperature of the gas, I expect the volume to decrease too. So we expect that balloon to get smaller. So let's calculate what it actually is. Because I have this before and after scenario where I'm making a change, that's a big red flag that I need to use the combined gas law, which is P1V1 over T1 equals P2V2 over T2. So I'm going to plug into our combined gas law. All right. So we're going to call this situation 1 and this situation 2 after we decrease the temperature. I'm going to just move this up a bit. All right, and get a little bit more room. All right, so plugging in our values, our first pressure and our second pressure is 1.04 atmospheres times our volume of 2.50 liters divided by our temperature of 260 Kelvin is equal to our pressure of 1.04 atmospheres. And since that pressure isn't changing, you could also use just like one of the simple gas laws only relates to of the variables. But I find it easier just to memorize one equation rather than 3. And our new temperature is 180 Kelvin. And so we're going to solve for that V2 right there. So V2 is going to equal 180 Kelvin times 1.04 atmospheres times the 2.50 liters divided by 260 Kelvin, oops, and 1.04 atmospheres. And when I plug all of that into my calculator, I'm going to get a value that is 1.7 liters. And if we look at that in comparison to the 2.5 liters we started with, in fact, the balloon got smaller, which is exactly what we expected it to do. So it's kind of like a mental double check on the problem that it is meeting our expectations for just gas behavior in general. All right, let's look at the next problem. So here I have a word problem about carbon dioxide in a can of soda. So let's extract some information from it. So what volume? So I need to figure out what volume is. So that's my big question mark. Would the carbon dioxide in a can of soda occupy if the number of moles of carbon dioxide was equal to 0.762 moles, the pressure was 0.977 atmospheres, and the temperature was 298 Kelvin, which is room temperature. So sometimes it's helpful to pull that information out and list it. So I don't know what my volume is. That's what I need to actually find in this problem. My moles will be 0.762. My pressure is equal to 0.977 atmospheres. My temperature is equal to 298 Kelvin. And I can pick out my R value because I know what my pressure units are. They're atmospheres. So I'll make sure that my gas constant reflects those units. And that's going to be equal to my 0.0821 liters times atmospheres divided by moles Kelvin. And then I'm using a gas constant that matches my pressure units. So looking at this, especially when you list it all out and you pay attention to the actual variables that are listed in this problem, I have volume, I have moles, I have pressure, I have temperature, I have the ideal gas law. The real big red flag for me about what equation to use with these problems is always if I see the number of moles included in the problem, then I'm going to use the ideal gas law. If I have something that's comparative and no moles are mentioned, then I'm going to use the combined gas law. So PV equals nRT, and we are solving for volume in this case. I like rearranging the equation first, but you can just plug in at this point as well. So volume is going to be equal to nRT divided by pressure, which will be my 0.762 moles times my 0.0821 liters times atmospheres moles Kelvin times my temperature of 298 Kelvin, all divided by my pressure, which is 0.977 atmospheres. And then at this point, it's really just plugging it into that actual equation, like your calculator, plugging the equation in. And when I do that, when I get a volume of 19.1 liters. So if you took all the carbon dioxide in a can of soda and like just had it fill a balloon, it'd be a big balloon. All right, let's move on to our next problem. So in this problem, we have a sample of fluorine gas. It's occupying a volume that's equal to 275 milliliters. It has a pressure equal to 945 millimeters of mercury. The temperature is equal to 345 Kelvin. And it wants to know what the mass of the sample is. All right, well, for this, we're going to need to use our ideal gas law, and we're going to need to use our molar mass as well. Now, this isn't asking about density, so we don't need to use our pressure, molar mass, density, temperature, and gas constant equation. We could kind of step back from that one. But what we're going to need to use is a combination of our ideal gas law and molar mass, because that has actual mass in it. And so what I can do is I can recognize right away that my variable that I have in common between these two equations is the number of moles. So I'm going to rearrange that. And now I have moles is equal to the mass divided by the molar mass. And I can now plug this value in here into my ideal gas law. And what I get then is that pressure times volume, it will be equal to my mass divided by my molar mass times my gas constant times temperature. I could rearrange this some more. The way you commonly see this written is as molar mass times pressure times volume is equal to mass times RT. Now I'm going to solve for mass. That's what I'm most interested in this problem, ultimately. So I'm going to rearrange that, set it equal to mass. You can also just plug into this version of the equation too, if you prefer. So my mass will be equal to molar mass times pressure times volume divided by RT. And now I'm going to actually plug in those values. So now I can use molar mass. And now the identity of the gas is important because we are looking at mass instead of moles. So I'm going to get the molar mass of my F2, right? So fluorine gas is fluorine is a halogen, so it would always be diatomic in the gas state as its elemental state. And that's going to be a molar mass of 37.996 grams per mole. Great. Now, before I plug in, I'm also going to convert my volume. I notice that I have units of milliliters. That doesn't really work for ideal gas law problems because my R value is going to have units of liters in it. So I'm going to convert this as well. We'll do that down here. My 275 milliliters will be converted into liters using 1 liter is equal to 1,000 milliliters. And so it'll be 0.275 liters. So all right, that works. I do need to pick an R value though, and I'm going to pick that based on my pressure units, which are millimeters of mercury. So my R is going to be equal to 62.4 liters times millimeters of mercury divided by moles Kelvin. All right, so let's now finally, I'll plug all this in. So solving for mass, I'll start with that molar mass. So 37.996 grams per mole times my pressure, which is 945 millimeters of mercury, and then times my volume of 0.275 liters. That's all divided by my gas constant using millimeters of mercury for my units. So that's my 62.4 liters times millimeters of mercury divided by mole Kelvin times my temperature, which is going to be my 345 Kelvin. Whew. All right. Let's plug all of that into our calculator. And when we do, we're just going to get the mass. So the mass is going to be equal to, sorry, it's on the next page. 0.456 grams. All right. That's how we calculate the mass of that fluorine sample. Let's move on to the last problem for this video. All right. So here we're looking at NO2 gas, and we want to know the density at 200 degrees Celsius and at 0.789 atmospheres. So now we are actually working with density. So this means that we can pull out that density equation that we had developed before, that pressure times molar mass is equal to density times our gas constant times temperature. Now, looking at this, we can take some of the information from our problem and set that up and figure it out. So our pressure is given to us as 0.789 atmospheres. Great. That means the R value we're going to use is going to have the units that have atmospheres within it. So our R value should be our 0.0821 liters times atmospheres divided by mole Kelvin. All right, so next we are going to try to figure out the density. So we don't know that. Our molar mass for NO2, I'm going to calculate that from the periodic table. And when I do that, I get a molar mass that's equal to 46.01 grams per mole. The last thing that I need to know is my temperature. My temperature is given to me as 200 degrees Celsius. So I'm going to convert that into Kelvin. I can't use Celsius in an ideal gas law problem. So to do that, I'm going to add my 273 and get a value that is 473 Kelvin for my temperature. Now I'm going to plug all this into that equation and solve for density. I'm going to rearrange it and set density equal to everything else so I can just kind of plug into my calculator. So that'll be pressure times molar mass divided by gas constant times temperature. So that density is going to be equal to my pressure of 0.789 atmospheres times my molar mass of 46.01 grams per mole, all divided by my R value, which is 0.0821 liters times atmospheres divided by moles Kelvin. I know it's annoying to write all those units. If you keep doing it though, I promise like once or twice you will catch yourself using the wrong R value, and like writing out the units is when you'll notice. And then temperature is 473 Kelvin. Whew, it's a lot. All right, so plugging this in, I'll get my density of my gas. And plugging into my calculator, I got 0.935. And those units, because we're working in grams and liters, will be grams per liter. And that's how we calculate the density, just using that equation we developed together.